Hey everyone, this video is all about our new paper MooTrack360, a novel fisheye camera dataset for robust multi-direct cow detection and tracking, which is about our new dataset meant for the development of new multi-camera, multi-object tracking solutions. So let's get to it. When people hear about livestock monitoring, they often think about
colors, RFID, accelerometer, or other on-animal sensors. Those systems can work well,
but they also come with real drawbacks. They require maintenance, they break, they need charging, and they are more invasive than many farmers would like.
Our goal is to push the alternative, non-invasive camera-based monitoring that can run 24/7 in real commercial farms.
And that is exactly what MooTrack360 is built for.
We have top-down fisheye camera views, large open stable environments, real-world challenges like occlusion, crowding, lighting changes, and fisheye distortion. At its core, the dataset contains 1,500 annotated images with over 100,000 cows instances labeled as standing or lying, plus a 1-hour full annotated tracking sequence, and also additional annotated video for development and analysis.
Now let's have a tour on what an open dairy farm actually looks like.
What you can see here is Area 2 within Stable 3, which is the largest scene included in the dataset, measuring in length 67 meters and in width 15 meters. This area will house around 60 to 80 cows who can walk around freely. In this barn, cows have access to beds for resting, water flues, brushes for grooming, and a feeding fence where food is delivered several times per day. In many barns, there's also an automatic milking robot. The cows decide when to go, typically around twice a day, and the system logs their visits. During summer, some areas also allow cows to go outside freely. With such a big area, the question becomes, how do you cover that with cameras in a way that scales?
Now, a lot of prior work uses multiple pinhole cameras with narrow field of views. This can work great in smaller and constrained scenes, but it becomes more painful once you have to scale up and build an actual application for 24/7 monitoring. Because it requires more cameras, more cables, more computing, more synchronization and calibration effort, and it is often just a tougher multi-camera tracking problem because the overlap is often limited.
We make a case for top-down 180 field of view fisheye surveillance cameras. As you cover more area per camera, you get larger overlap between views, and that overlap is extremely helpful for inter-camera association. Our cameras are also ceiling mounted and records at a resolution of 2944 by 2944 at 10 frames per second. For this area that I showed before, we only need 4 to cover the scene nicely.
Now, a critical element for 24/7 monitoring is nighttime. Some barns dim the lights, while others turn them off completely. To handle that, we choose cameras with built-in IR illuminators, so they can switch into an infrared-assisted mode automatically during nighttime. While fisheye cameras give you great coverage, they do also come with their own set of challenges, namely greater distortion. So camera calibration is a must. For fisheye lenses, the standard pinhole model isn't a great fit, therefore we choose the double sphere camera model, and the key idea is that it supports accurate projection and back projection for wide-angle fisheye lenses with a compact parameterization. Now, to calibrate the intrinsic in practice, we actually follow the same procedure as described in the original paper.
We record a custom able grid for multiple viewpoints. We store the frames inside a ROS pack and run calibration through Basalt. This is repeated for each camera, and the one with the best reprojection quality is then picked for each.
For the intrinsic, we want each camera pose in a shared coordinate system, so we can do ground plane projection and reason about where cows are in the stable. To achieve this, we measure the area using laser distance meter and level tools. We place several of these able tags as reference points across the scene and solve the camera pose to align everything to a consistent global floor plan coordinate system. Finally, we provide not only the calibration parameters, but also a semantic floor plan with the beds, the water, the bushes, feeding zones, milking robots, and so on, plus adjacent mapping, so it's easy to compute region occupancy statistics like how many cows are in the beds at the moment or so on.
And now for the annotation, which is the core contribution. And here we made one key choice. Instead of only labeling with the label cow, we label 2 behavior relevant classes, standing and lying. That's a simple label set, but it's immediately useful for welfare monitoring because lying time and lying patterns are strongly linked to comfort and health indicators. To keep the dataset high quality in a challenging fisheye scene, we also introduce a practical idea, region of interest masking. Because of the increased field of view, a lot of outside area is also included, so therefore we apply a camera-specific mask, so we only train and evaluate on the stable region we care about. And we avoid penalizing the model for cows that were never meant to be annotated in the first place. Then comes the training pipeline. Here we provide script for the masking and cropping to the active region as described before, and a two-stage augmentation pipeline. First, different sets of geometric transformation are applied, followed by sets of photometric augmentations to simulate some of the key challenges observed and to train an even more robust model. And now to the actual evaluations.
And now for the detections, we benchmark several families of models, including multiple YOLO variants, transformer-based real-time detectors, and classic baselines, to give the community a realistic starting point. The evaluation setup is consistent as well across the models. 250 epochs for training, 800 by 800 for the input image size, and a split of 80 to 10 to 10. And it should be noted that the testers only use the original image to simulate a real-life case scenario. And just glancing over the results, a clear pattern shows up that you could have might predicted. The smaller models run significantly faster, but are less accurate compared to the larger models that are more accurate, but are significantly smaller.
And one extra detail we added is a per class normalized confusion matrix. Typical confusion matrices can be misleading when background isn't explicitly labeled. Our normalization is designed to show per class how errors contribute between confusing standing versus lying and missing cows entirely. That makes it easier to see whether the model is failing because it can't separate behaviors or because it's missing detections on occlusion and poor lighting or likewise.
And now for the tracking evaluation, we decided to annotate a 1-hour video sequence with 50,900 and 321 frames from a single camera area. In that sequence, the scene starts with 3 cows, and as time progresses, more cows enter through a gate until there are 8 cows present at the end.
We evaluate trackers using TrackEval, and for the detection model, we use the trained YOLO V11 large model from before, as it offers great balance between accuracy and inference speeds. And
now the headline result is that ContraTrack performs best overall with the highest HODA and IDF score and only one ID switch over the full hour. And the last part is very crucial because some trackers can score high on motor while still constantly swapping identities, which is unacceptable if your goal is long-term welfare analytics per cow instance. So the takeaway is, even with strong detectors, robust long-term identity preservation is still one of the hardest open problems in real farm tracking, especially once you move from one camera to many cameras. So now to kind of wrap things up, with MooTrack360 we introduce a new high-quality dataset for the development of new multi-camera, multi-object tracking solution with a focus on livestock monitoring.
And compared to other datasets who focuses on pedestrian, this focuses on livestock monitoring.
Thanks for watching, and if you have any question or ideas for what you'd like to see next in MooTrack360, you're more than welcome to leave a comment or reach out on the GitHub repository. Bye!